Hi, my name is Christopher Sprague. I'm a PhD student at the Robotics Perception and Learning Department at KTH Royal Institute of Technology in Stockholm, Sweden. In this presentation, I'll present our paper, Learning Dynamic Objective Policies from a Class of Optimal Trajectories. In this presentation, first I'll explain our motivation, some common control approaches, and how this paper extends from our previous work. Secondly, I'll explain the generation process of the data used to train our policies. Then, I'll present two examples, an inverted pendulum swing-up and a low-thrust spacecraft orbit transfer. Finally, I'll present some quantitative results of the efficacy of our approach and some key takeaways. Our primary motivation for this paper is that it would be useful for autonomous systems to be able to change their control objective online in response to unforeseen events. Such a situation could arise in a system that is minimizing time of travel, but all of a sudden discovers that it has a battery failure and needs to switch to minimizing effort. Or in a system that is minimizing effort, but all of a sudden needs to reach its destination earlier than expected. Or perhaps there is an external event that requires a certain balance in objectives, like the gray trajectories illustrated here for the spacecraft orbit example, which represent different trade-offs between two different objectives. In all these cases, an optimal controller that can adapt its behavior online is needed. However, for nonlinear systems, finding a closed-form optimal control solution for even a single objective can be challenging. A common approach to circumvent this is to compute an optimal trajectory offline and follow it with a lower-level controller. However, this approach suffers when unforeseen events require a change in the objective, or lead the system out of the controller's region of attraction. One way to ameliorate this is to employ model predictive control. This method grants reactivity in response to unforeseen events. However, its iterative solving process can be computationally expensive and result in suboptimal solutions, as it does not consider the full time horizon. Through rapidly developing approaches that mitigate these issues are reinforcement learning and imitation learning. In these approaches, online computation is minimized by learning the optimal controller offline and employing it online. In systems where optimal demonstrations are available through trajectory optimization, imitation learning is often a more straightforward approach, due to its greater learning efficiency. This is how we proceed. As far as we can tell, imitation learning has been unexplored in the context of objectives that can change online. In our previous work, we generated training data for imitation learning by solving several trajectory optimization problems using homotopy continuation between two control costs. One easy to solve, which for example could be a quadratic cost, and one difficult to solve, which could be an absolute value cost, which often results in a difficult to approximate bang-bang control sequence. In this process, we would first solve the problem with the homotopy parameter given by alpha equal to 0, as illustrated by the solid line in this figure, which represents the optimal control sequence for this parameter in the inverted pendulum example. Then we would increase alpha slightly and quickly resolve the problem. As illustrated by the gray lines in this figure, we iteratively continue this process until alpha equals 1, at which point the optimal trajectory is obtained under the difficult cost function, as indicated by the dashed line in this figure. We iterated this process over many different initial states to obtain two datasets of state control pairs, corresponding to the easy and difficult cost functions, which we then used to train two separate policies. In the presented paper, we extend this approach by keeping the state control pairs and their corresponding homotopy parameters along the intermediate trajectories, to see if we can train a policy to learn the optimal control with respect to the homotopy parameter. In our paper, we consider autonomous systems whose dynamics vary only with the state and control. In our trajectory optimization problems, we consider costs that are determined by the controls taken over time. Given an initial state, decision vector guess, and homotopy parameter as arguments, we can solve the trajectory optimization problem with prescribed boundary conditions to obtain the optimal decision vector. With the initial state, decision vector, and homotopy parameter, the optimal trajectory of states and controls is straightforwardly obtained through numerical integration. In our paper, we use Pontryagin's maximum principle with the shooting method to solve this problem, where the decision vector variables are the initial costates and trajectory duration. However, if we only had a black box dynamics model, for example through system identification, we could instead use direct collocation methods. As previously described, we use a homotopic cost function and iteratively solve the trajectory optimization problem with increasing values of the homotopy parameter alpha. But in contrast to our previous work, we keep the intermediate solutions to obtain a convergent series of trajectories, denoted here by T, If at any point along the homotopy path the optimizer fails to converge, alpha is decreased to a value greater than its previous best value. This ensures that there is some sense of adaptivity to the solution's sensitivity to the change in alpha. Overall, this process is efficient, as solutions for similar values of alpha are similar, so convergence is quick. A similar process is performed across the initial states. From a nominal optimal trajectory, we iteratively perturb the initial state and solve the problem, to obtain a series of solutions. If at any point the optimizer fails to converge, we resolve the problem with a smaller perturbation. If the optimizer is successful, we increase the perturbation size slightly. These conditions ensure a sense of adaptivity to the solution's sensitivity in certain regions of the state space. Similarly to the homotopy parameter, solutions are similar between close-by initial states, so convergence is quick. In practice, we apply several instances of the state homotopy algorithm in parallel upon a nominal optimal trajectory. We then apply the criteria homotopy algorithm in parallel across each of these solutions to obtain a massive data set, as shown in this figure for the spacecraft orbit case. With this dataset, we then train a multi-layer perceptron to learn the mapping between the state homotopy parameter pairs and their corresponding optimal control. The result is a parametric feedback controller, whose homotopy parameter can be manipulated online to change its behavior. In our paper, we illustrate this approach in two common autonomous dynamical systems. The first of which is a non-dimensional inverted pendulum, with one homotopy map, between quadratic cost at alpha equals 0 and time cost at alpha equals 1. Here we illustrate the homotopy map of the inverted pendulum's endpoint along the nominal optimal trajectories. The solid line represents the optimal trajectory for only quadratic cost, and the dashed line represents the optimal trajectory for only time cost. The gray lines represent the optimal trajectories for the intermediate values of alpha. As a step up in complexity, we also considered a low-thrust spacecraft orbit transfer between Earth's and Mars's orbits. In this system, we nominate more complicated boundary conditions. The first is the transversality on the final mass, which indicates the fuel consumption. The second is the transversality on the position along the final orbit, which is a manifold of the states and co-states. As another elevation of complexity, we also add a secondary homotopy parameter to the cost function, denoted here by beta. This yields three different homotopy maps, as indicated by this figure. One between quadratic and effort costs, one between quadratic and time costs, and one between effort and time costs. In our paper, we only use beta intermediately to attain solutions under effort and time costs, as their solutions are discontinuous and thus difficult to solve for. We keep the intermediate solutions for every alpha to see if we can learn a continuous map between these discontinuous functions. Now let's see how well our approach performed. We trained multi-layer perceptrons of various breadths and depths on the datasets of the inverted pendulum swing up and the spacecraft orbit transfer. We evaluated the regression performance on the training sets and the validation sets, which are composed of 10% of the original datasets. Across every architecture and dataset, we achieved good performance in the data regression task, with results generally getting better as architecture size increases. Since success in the regression task does not necessarily guarantee success in the control task, we simulate the policy control trajectories of each system for the duration of the nominal optimal trajectory. After doing so, we compute the true optimal trajectory between the endpoints of the resulting trajectory. We compute the policy trajectory optimality as the relative difference between the cost of the policy-driven trajectory and this resulting optimal trajectory. We do this for various breadths and depths of networks like before, and for a linear spacing of homotopy parameters. In general, the performance improves with either increasing network breadth or depth. The best overall performance was achieved in the spacecraft example, where less than 1% of the optimality difference was achieved with most networks. We suspect that performance is worse in the pendulum example due to the saturation of its control when the cost homotopy parameter was less than 1. Despite this, our approach was successful in both cases. The key contributions of our paper were an efficient data generation pipeline to produce optimal demonstrations across various objectives and initial states, and parametric policies that continuously represent the homotopies between optimal controls. The result of our approach is a parametric controller that can change its objective online, as we illustrate in this figure of the inverted pendulum's control sequence, where the homotopy parameter is incremented at different points in time. The case of the spacecraft orbit transfer was unique, in that it required learning a continuous mapping between two discontinuous controls, resulting from effort cost and time cost. Though our networks learned this mapping quite well, they generated noise around the control switching points. We suspect that this could be improved with regularization of the network weights. Additionally, since the policy trajectory optimality of each network was not uniform across homotopy parameters, we think performance could be improved by penalizing the training loss based on this distribution. That concludes our presentation. Thank you for watching. If you have any questions or would like to collaborate, please do not hesitate to get in touch.